Hello, everybody. Welcome to our PLC2 webinar. My name is Eugen Krasin. I'm your trainer today. Let's start. This is the second part of our FPGA circuit design presentation. In the second part, I'm going to show you some some examples how to implement different kinds of interfaces. I show you how to design and constrain low speed and high speed ADC interfaces. So I just selected ADC because it's a very common application, and especially for the ADC we do have low speed ADCs, but we do have also high speed ADCs to interface with. So that's it's actually a very nice application here. That's what I selected. Of course, all the information I present here is can also be applied, of course, to other kind and other type of applications. Okay, that would be the agenda. Very to start with, I would like to review some of the FPGA I/O resource, because for the interface we are talking about I/Os. We have to take signals in, we have to provide signals out of different kinds. So I would like to give you a very short overview about the I/O resources, and also to introduce to you two kind of interface types: source synchronous and system synchronous. And actually in this webinar, I will show you two examples. One is a source synchronous, one is a system synchronous application. Then I will show you some interfaces here. This means first I would select a low speed interface. That's actually the device, analog devices, ADC here, and I will present actually the first alternative, and well, the second alternative, I just will mention it, not really presenting, and the third alternative. So this means how can we implement this circuit using different approaches, single clock domain or maybe two clock domains. What are the advantages? What are the disadvantages? So this would be the low speed, okay? But then just to show you also, for let's say more sophisticated application, I will also do a very small design actually to interface high speed interface. In this case, I will select the ADC 9252 device to show you what's going on. So, but first, let's actually look to the FPGA resources. So in this case, I'm going to talk about the resources. This means, how does it look like? Well, our FPGA, let me draw maybe here. Here we go. So that's actually the device, FPGA. So and then, so this is inside the FPGA. Okay. So we do have some, so we do have some slices or CLBs. So let's show it here. But and the peripheral right here, okay. So we do have so-called IOBs. Okay, so these are the IOBs. So this means these IOBs depends on the package. There could be almost more than 1,000 actually. So this is one IOB, and using this IOB, I can have an input if you like, or actually an output, or of course a bidirectional. Okay? So this means I can also do something like this, and this IOB, this component is actually this component here. Oh well, that's actually the connection to the FPGA. So this is the component. Okay, so this is here a pad right here, and this is the connection to the physical connection to the package. Okay, so that's actually such a pad, and this pad consists of actually two parts. So we do have an input part, we do have an output part, and of course bidirectional. Or two neighbors of the pads also can be combined to build differential signals. So in this case, if we don't need a differential signal, so these are independent. But if you need a differential signals, then this could be connected together. This means such IOB contains input delay block, output delay block, input SerDes and input logic, and output SerDes and output logic. And we will actually talk a little bit more in detail about this different kind of resources. First, let's talk about the I logic. So the I logic, this means I do have here a pad, and I would like to use this as an input. So in this case, the I logic, an option, I can, if I like, actually use the internal flip-flop, which is right here, not inside the FPGA, right in the peripheral cell. So this flip-flop could be double data rate, could be, if I like, single data rate, or I could even bypass this flip-flop. So this is part of the I logic. This means I can, instead of using some resources in the FPGA fabric, I can use it actually in the peripheral cell, okay, for the inputs. The same for the output. If, in my case, I have, let's say, an output, I need a flip-flop, which is actually, output a signal. So instead of using a flip-flop inside the FPGA fabric here, I can actually move this flip-flop in the peripheral cell. So I can save resources and save area, and makes it a lot easier for the software to implement this, and also I will gain and I will improve my timing in order to do this. So this is called the O logic, output logic. Again, it could be single data rate, it could be double data rate flip-flop, or I can even bypass this flip-flop by using just a combinatorial output. And of course, in this case, I need two flip-flop because I can also have, let's say, a tri-state output. So this means one is actually output the data, and one is actually to control the output enable of the output signal. So in this case, I have two flip-flops here. So that would be the O logic part. So, but now I have very, very special application. It's called SerDes, iSerDes and OSerDes. So first, iSerDes. So what is an iSerDes? iSerDes is an input serializer, deserializer. This means I do have usually a high-speed incoming data, high-speed, really high-speed right here. And instead of processing the data here, I just do a serial parallel conversion right here in the pad, and then provide a parallel output. Okay, so this makes it very easy for me. And in this case, again, I can implement very, very high-speed circuit because everything is done right here in the peripheral cell. So I don't have actually to route high performance and high-speed signal inside the fabric. Okay, so that's called ISO. I will actually use this application. I will use this in my very last example by when I do a connection of the high-speed ADC. So in this case, I will use iSerDes. This means this serial parallel conversion, could be done for double data rate, could be done for single data rate. And the question is, okay, what's the size of this serial parallel conversion? So in this case, we could do, for single data rate, we can convert serial to parallel. So this would be the output bus here, data size of the bus. Double data rate, it's a little bit less. So now you can say, well, that's not a big deal. So I need maybe more wider buses. Yes. So in this case, remember, we can combine two neighbors. We can combine. So this means we can actually combine the enabled iSerDes to even form more wider connection. Okay. Again, a little bit later, you will see the application here. And the same OSerDes. So in this case, I would like to output a high-speed serial signal here. Okay. So, but in this case, I don't like actually to generate a high-speed signal inside the FPGA. No, I just take a parallel n-bit parallel data and just connect the parallel data to my pad, and let the output service, so this is a parallel serial, parallel in, serial out, to actually convert the data and do it exactly in the peripheral cell. So in this case, of course, we do have two kinds of servers. One again is actually for the data, and one again is, of course, to control the output enable. So in this case, my application don't need all servers, but maybe for high-speed DAX or whatever, that could be a very, very nice application here. And again, if I need more wider buses, I can combine, two neighbors in order to form even more to get more widths of the parallel data. And then I have O delay and I delay. This means that's actually, I would like to output a signal here, but for whatever, this would be maybe output signal here. For what reason? I would like maybe to fine tune. I would like to insert a delay here. So this would be a delay. Okay. So for output would be O delay. And the same for the input. So I have maybe an input here, and I would like, to add maybe a delay here again, before I do a processing here. So it could be fine tuning. This could be, to adjust maybe the skew and on the PCB, whatever. And also I will use again the delay in my example. So very, very nice. We can program and assign different values for the input and output delay here. For example, well, let's assume that would be, I have input here, okay, and I would like actually to take the data and to register the data here. Now, PVT, this process voltage temperature, I have a slow and fast. This means that would be the worst case. This means bad process, very low voltage, very, very high temperature. So the FPGA is slow. In this case, fast. It is a very nice process, very good process. It's a very high voltage and it's a very low temperature. So in this case, would faster. But I would like to have get always the data captured on this edge. So in this case, maybe for the slow, I will capture the wrong data. For the fast, I will capture the proper data. So what I can do, I can actually use here an I delay here to compensate for the slow and fast stuff. In order to, if you don't need this maybe for a lower frequency, but if this is a high frequency, that would make sense to do this. So we can do a dynamic adjustment depending on the PVT, or we can also do the skewing. This means again, this would be my FPGA right here. Okay, and I do have maybe a device. This device provides me, let's say, 3 signals. One is R.0, 1, and 2. Okay, and I will capture the signals here. Now, because of the different delays on of these traces on the PCB, okay, the data maybe R.0 will arrive a little bit later. The data R.1 will arrive earlier, and again the data 2 will arrive somewhere here. This means I'm not able to capture the data at the same time point. So what I will do, I will actually input some delay here, some delay here, some delay here, and I just will move all the signals to the proper position, so will capture always the proper data. Okay, so that's called a D-skew. So that's also an application we can use here. Okay, so you see, that's a lot of stuff, and it makes sense. If you need more information, just look to the data sheet, look to the description, and you will see how easy it is actually to use this IDLA blocks, for example. Okay, so but now you talk about this I/O resources. The question is, how can I use this? Well, some of the resources can be inferred. This means you describe, maybe you will have an input here. Here we go, something like this, and you would like to use maybe a flip-flop right here in the peripheral cell. So that would be an IOV. So if this is your, if this is what you want, then you can simply describe it in using the HL Verilog, and this will be inferred. So that's okay. That's done fully automatically for single data rate. For the input data rate, for the double data rate, it could be done, but I don't recommend this really. So whenever I need a double data flip-flop, just do direct instantiation of this component. But the output double data rate cannot be inferred. You have to do a direct instantiation. And the same applies for I service and O service. You have to do a direct instantiation of the components. You cannot infer this by describe this using Verilog or VHDL. Just for your information. Now, talk about the different kinds of interfaces. Now let's talk about the source synchronous and maybe the system synchronous. So what is a source synchronous interface? You see, that's a source synchronous interface. That's my FPGA. Here we go. I do have a component, usually that's maybe high-speed ADC, which runs with the own clock and provides a data. There's some kind of data here, okay, and provides the clock. Okay, and this is connected to the FPGA. This means inside the FPGA, I need an interface which actually takes the data as this clock to interface, and then usually we need another clock to process the data further, to do further processing. Okay, so this is called the source synchronous. This means the source is providing the data. This is the, this is usually the choice for implementing high-speed connection is always source synchronous. Okay, and one of my example, the last example actually, I will use exactly this kind of interface. So the source, and this is just to give you just an overview, not a big deal, to show you how what is the type of interface which could be here. You know, the relationship between clocks and data. For example, it could be a single data rate, aligned to the edge. So, and this means what's all about. Just to give you an idea, this is actually your job. This is your job. You need to understand this is the interface type, and then you have to look to the data sheet. And in the data sheet, you have to look for the delay of the component. What is the delay? What might be the minimum and the maximum delay? Okay, that could be minimum maximum delay here, and you have to specify this before you actually do and run the implementation. The tool will actually take the minimum and the maximum delay here, and will find a proper solution how to actually clock the data in the proper position, how to capture the data in a proper position. So it could be also double data rate, for example. That's what the single data rate is, with double data rate. So these are the typical application of what you can do. So this is could be, you know, center line, for example. So that's actually what I will use. I have a clock, the ADC, for example, and this ADC provides me data, and the alignment is, you know, the rising edge is in the center of the data eye. Okay, so and then we have actually defined, look to the data sheet, define, take the values, specify the values, as a timing constraints, and run the implementation. That's the mechanism. What is the system synchronous? Well, the system synchronous is a little bit different. For the system synchronous, I do have just one clock in my system. Here we go. And this clock is actually used to drive an actual component, but it's also used by the FPGA to, you know, to input the data. So that's it's very easy. It's very easy interface here. But what is the disadvantage? The disadvantage is the speed of a system synchronous interface is usually much less compared to the source synchronous. Okay, so this means if you run here maybe 100 or maybe 200 megahertz, that's actually pretty fast for system synchronous, but for source synchronous, you can run with 1 gigahertz. Okay, so that's the difference. So this means for simple application, the system synchronous might be a good choice. So in this case, also the same. We do have exactly the same situation. Just again, a diagram here. We are responsible and say, okay, if this is the clock, what is the best mean time, what is the max time? So this is mean this is uncertain region. You have to specify everything here, and then it will be the timing constraints, and then that will implement this. One of my next webinars, I will actually talk exactly about how to specify the timing constraints in order to describe the interfaces. This will be one of my next webinars. Again, so we do have system thing. I just go back, single data rate, aligned to the rising edge, could also be single data rate aligned to the falling edge, could be double data rate. So all kinds of interfaces are available here. You need to understand, well, that's my component. That's the interface I need to implement. Then you have to look to the specification, and then you have to extract all the values from your data sheet and use the values in describing your timing constraints file. So now let's actually look to the very first example. It's a very low speed interface 7476. That's a very simple stuff. So just a data sheet. You see that it's a SPI, so we do have a clock and data, and that would be the format. You see, we do have here a chip select, and when a chip select here, and with a falling edge, the ADC starts to provide the data, and my FPGA will actually need to capture the data. Usually we capture the data here on the rising edge, and the ADC will, as you see here, actually generate the data on the falling edge. So you will see all the timing specification, and again we extract the parameter and put it to our timing constraint file. So that's actually the device. And the speed is not very very high. So it's called a 12-bit high speed. Well, but what is the high speed? You see the maximum frequency here is 20 megahertz max. Okay, so this is actually not really high speed. Okay, so the question is, how can we define this? So alternative one. So again, this is the specification. So alternative one, what can I do? Well, I can do something like this. That's very simple. I just define my FPGA. So that would be my FPGA right here, and I just take maybe 120 megahertz here, and I just define a very simple clock generator. It would be a counter, and just provide the clock here. That would be the output, 20 megahertz, for example, the output, and this would be the external component here. And then I just take the clock and use the clock to control the state machine, to provide the interface, actually SPI. So this is actually for the SPI handling here. You see what's so special here? Well, the special here, it's a 2-clock domain. So this is clock 1, okay, but this is clock 2. So we have 2 clocks. You see, system clock and the SPI clock. Well, it's very easy to do this, but we will have some disadvantages, because these clocks are not really related. Even if you have a counter here, okay, because of the delay, the phase relationship between this clock and this clock is not really known at all the time, and it will vary according to the PVT. So this means in this case we need some kind of let's say of a synchronization circuit between the system clock and the state machine here, because you cannot simply connect this together. You need some kind of CDC crossing mechanism here. So that would be actually the idea. This means the clock generator would be simple, a counter which defines, you see, that would be the sys clock. Here we go, the sys clock right here, and you see, and this would be the clock, and you see it's a then it's simply dividing the input clock here, and that's actually the output. Okay, and by using the formula here, you can easily select and change the frequency you would like to get. So that would be the clock generator. Well, if I go back here, and the control state machine, well, it's also very simple, because just remember, what is a control state machine doing? The control state machine actually, whenever we have a start, we like to get the data, then the state machine actually generates a sync signal, okay, and then runs in a loop until it get all of the bits, and when everything is there, then it will generate the the output valid and the data ready. But again, just remember, because this is the system clock, but this runs with the SPI clock, we need here a sync stage in order to to avoid the metastability. Okay, that makes a little bit. It's not really nice, but it's very simple. So this means in order to so that's actually the idea of, if I go back here, idea of having this kind of synchronization circuit. Otherwise, it will not be possible. Okay. So this means, because we need to have a minimum width of the signal, because in order to synchronize this with a lower signal. So that's a little bit, it's not nice, but it's the disadvantage of this kind of application. So, and in order to find out, well, how does it work, we just do a interface, a test bench application. So what I simply did, so this would be my FPGA right here, okay, and then in the test bench, this is the system clock. This is basically the start signal for the sample. That's actually FPGA as we described. That's actually a VHDL model, and this is actually an analog source which is connected to the model, and then actually we can connect this to the model and read actually the analog value. So if I do this, let me just prepare this already. Alternative 1. You see, that would be my alternative 1. You see, that would be here, my FPGA. Here we go. Start and data on the connection. This is the SPI connection to the ADC. And that's the application internally control user logic and the clock generator. So in my test bench, here we go. The test bench actually consists out of instantiation of the FPGA. Well, this is the model of the 7476. So this is just, I described the model here in order to be able to run the simulation. And then I defined here I call this a sensor. This is basically the supply of the analog voltage here. So that's actually this one. So this is a sensor, analog voltage, and then we just convert in this model, converting analog to digital, and we are just reading the digital. So if I just go here and start this, run the simulation here, then you will see that here we go. Let me get a little bit more here. So if I just run a little bit here, I don't know, maybe here. You see here, so that's actually, that's SPI, that's SPI connection, and here you see that's actually the analog input value, which is the sensor output, and this is actually the acquired data from the ADC, and you see that's what let me again run a little bit more. So here we go. And this is actually now a complete simulation of how to, how to use this. Very, very, very simple, and costs you just a few flip-flops to do this. Okay, alternative one, very simple. Now let's actually go to alternative 2. So alternative 2, it's actually the same, very, very identical to the alternative 1. So therefore, I will not really look to it, but tell you what is the difference. The difference is I don't use a counter here, in order to define the SPI clock. I can use a PLL. You see, it's just a PLL. I'll say, okay, maybe, I don't know, maybe 120 meg in, and maybe output 100, and maybe this output is 20, whatever. So that's the only difference. I just replaced the counter clock generator by a PLL. That's the only difference, okay? Nothing else. Exactly, so that's what I told. Exactly the same, just the clock generator is different. Well, in this case, why is this maybe of interest? Well, because we use a PLL, you can very easy define that this clock phase is exact, or this clock is exactly in phase maybe with this clock. So because this is in phase, we can avoid a clock domain crossing circuit. That could be the advantage, okay? But that's maybe the only advantage here. So I will not concentrate on alternative 2, but I will concentrate on alternative 3. So what's alternative 3? Well, in this case, I'm using a single clock domain. You see, just one clock. So this means also this clock, which is actually SPI clock here, is not really a clock for me. It's just a signal. That's a signal. It's not really a clock for me. My clock is just the clock, my system clock. So everything is just one clock. Now it's very simple, and very, very powerful, because I have just one clock. I have just one single clock domain, and in this case, we are very flexible in terms of changing the application, changing the time point where something needs to be sampled, because just one clock, we can shift the sample pulse very, very simple and easy. So this means, in this case, the clock generator looks a little bit like this. You see that? That's just a data. It's not really a clock. By doing this, we just define a clock. Here we go. This identified here in red. But you see, I defined two signals. Here we go. One is H low, one is H high. Simple indication. It's synchronous to my master clock. Hey, now there's a rising edge on the external signal. Now that will be a falling edge on the signal. Okay, but it's not really a clock. I'm just using these signals, and these signals now are interpreted by the state machine to capture, for example, the data. That's the one and only difference. But the kind of the state machine is the same. The only difference is this state machine does not run with a clock. This state machine runs with just system clock and just look to the edge, high rising edge, falling edge, and then this is how the state machine actually is controlled here. And again, the test bench is very similar. Again, the clock, and again, you see here, this is just a single clock domain. And again, of course, the same setup here, because it's, of course, it's neutral for the external component here. So now, again, let's look to alternative 3. So that would be an alternative 3. You see, in this case, I just have here just one clock. There's just one clock here. There's no, you see, well, I just use a PLL just to condition the input, one input clock. This is just, but not really a clock generator. You see, no clock. This clock generator provides a low and high. So again, if I run the simulation here, let me run it here. So if I run the simulation here, Here we go. Let's relaunch this. Then we'll see actually the same result here. So now you see, it's actually the same. But now I have just one single clock. Makes it very, very simple and very, very powerful. Okay. And of course, again, here you see that's the model of the external sensor. There's few lines of code, very, very easy. And there's actually the output here. So that would be alternative 2. Now let's look to the alternative 3. To the high speed. So this was the low speed. Now, well, before we go to the last example, let's do just a comparison. Okay, so what's a comparison? You see, alternative 1, I do have 2 clocks. Because I do have 2 clocks, I need to care about the clock to image crossing. Okay, this means I need to describe it. I need to place the proper timing constraints. I need actually to define synchronization circuits. Okay, the timing constraints is you have to put some effort here because we do 2 clocks. We have actually to define all the clocks here, and of course we have to define the clock domain crossing paths, and that makes a little bit more difficult. Well, it's quite flexible, and design is also good. Alternative 2, that's the same now with PLL. You see with PLL, we do have 2 clocks, yes, but we don't need to care about the CDC because they are in phase. That's what the PLL is doing. Everything is done automatically, but the design is, the flexibility is poor. Why? Because we use a PLL. This means the relationship is fixed between the clocks, and so it's not a really good flexibility. Okay, but it's very nice to design. Alternative 3, just 1 clock domain, no CDC, and very good flexibility, and very good to actually also to design. Of course, we need to do a little bit more. This is done everything full automatically. We have to define a little bit more here, but it's good performance. Now let's look to the high speed interfacing. For the high speed, that's actually this ADC 9252. It looks like this. You see, it's a high speed ADC. It provides a 14-bit 50 megasamples ADC. But this is done serially. Okay, so this means we provide input clock. So this is the input clock of what is actually generated by your FPGA maybe, and I think the ADC actually takes the clock, multiplies this by 7, okay, and outputs in double data rate the data. Okay, so this means you see for one period, okay, half of the period, okay, we get here 14 bits, you know, because this is multiplied by 7, double data rate. So this means these are 14 bits. And just to have first, the idea, where are the samples? Because there is no start, there is no stop. It's just a stream. We got this frame signal. So this means this is one sample, this is one sample, this is one sample. It's absolute high speed. Okay, we can run 14-bit up to 50 megasample and transfer this, serially. So this means that the frequency here is, in this case, would be the 350 megahertz, for example. Okay. So now, that's how to interface this. So this means the idea is, you see, that's ADC, and it output a clock. It's a high-speed clock. And then outputs data, which changes right here. Okay, change the data. No, on all of the edges, the data is changing. So now, and now we need to take this and go to the FPGA. Let me move this one. So to go to the FPGA and just receive the data, and this, of course, application for this iService. So in this case, for the iService, that's actually the idea. You see, that's the ADC right here. The ADC provides the high-speed clock and the data. We know that the ADC is sending the data in double data rate, and 14 bits are transferred with 7 clock cycles. So this means, so this is the high-speed clock. Now we take this high-speed clock and then we just shifting in the high-speed data right in shift register. At the same time, we just take the clock and just go to a very special clock buffer inside the FPGA and say this is divide by 7, div by 7. So this means that now we have an in-phase relationship, high-speed clock and a low-speed clock. This means this would be the high-speed clock here. And this would be the low-speed clock, which is divided by 7, something like this. So this means we just shift in 14 bits, and then we take, and this would be here, 14 bits. And then we take, with this edge, we take the data and provide it to the FPGA fabric. Okay, and this is this iService, you know, just shift in and take the data, because we know 14 bits, double data rate. So we just take the clock path and say, well, this is divided by 7. And now we do have a very, very fixed relationship right here. Okay. So this means now that would be the application. There's no logic, because everything is actually done in the IOB. You see, that's the high-speed clock. Here we go. That's the frame signal. Because why do we need a frame signal? So let me just go back. The frame signal identifies where is the sample. So this means if I take this clock and divide it by 7, the clock could be related somewhere here and here, but I don't really know where's the sample. So therefore, I just take the clock and read in the frame. Then I look to the position that the frame is 1 1 1 1 1 1 1 1 or 0 0 0 0. Okay, so now I know, oh, that's the complete frame, because this is the frame, and I take the data. So I need to read in the frame. Okay, and this is actually right here. Now, so this is the high-speed clock, which is used, you know, to clock the service. But this is the buffer which divide by 7, take the data from service and capture it. So this is my divide by 7 clock. The problem is, this is the input clock. The clock and the frame are related to each other because of the data sheet. But this buff IO and this buff R, these clock buffers, they introduce a delay. That would be not a big problem if you have a low-speed application, but in this case, this is a high-speed application. So this means now the delay matter. So we need to compensate this delay. You see now, we just put a delay right here, which is the same as the delay here. So we just have the same situation, clocks and frame, the same situation as outside. Okay, and then we just, because we need 14, so this is 14 bit. So we just take 2 iServices, one master, one slave, and then combine it two. Now we just read in the data. Now there's a small state machine. You just look to the frame, and whenever the frame is 1 1 1 1 1 1 0 0 0, we just take the data. So this means we are synchronizing. And this everything is IOB. Because we synchronize it for frame, at the same time, when you synchronize your frame, you also take the data. It's the same situation. We are not just compensating the delay for frame, we also compensate the delay for the data. This is also IOB. And the control actually look, well, now I found the frame of the data, and now everything is synchronized. And this is very, very small state machine. Just say, okay, now the interface is complete, and which I just to show you the simulation, I just enable a FIFO here. So this means if the synchronization is not done, the FIFO is disabled, it's not active. The control logic found the frame and said, now I'm synchronized. Okay, now the FIFO is active and I can actually get the data from here. So you see, there's everything is done in the peripheral cell. So this means the logic, just few lookup tables, almost nothing, because everything is done in the peripheral cell. So this means if I look to again to the situation, so this is the clock, and because of this clock buffers, we introduce a delay. We need to compensate this, and you see here, that's actually this one. It's actually the external connection, P and N. Okay, and if I look to this clock, you see this is this one. You see that's actually the delay. That's delay from here. That's the delay, because this is here, but this is actually this line here. You see, and then we have to and that's actually we have to compensate this. This means now we insert a delay, which actually is actually the same amount of as here. And now the relationship of this clock and of the data, the relationship here is exactly the relationship here. And now we again actually take the data. That's the whole idea. And that would be the test bench. Again, I just do the same. I have the model of this high-speed ADC. Here we go. I do have again the sensor here, and that's actually the logic. And then just to run the application, I do have here addition clock. This is my system clock. In this case, you see there's a typical application for source synchronous, because now we have actually two clocks. One clock is actually used for the interface, and then the master clock is actually used for read the data. And that's a standard application always for for source synchronous application. We do have always a crossing, a FIFO to cross between this clock domain and this clock domain, because they are not necessarily identical. Of course not. So in this case, that would be 350 megahertz. In this case, this would system clock 100 megahertz, whatever. So now, actually, let's look to this. So if I just go to that would be my application here. You see, that would be my top design. And you see in my top design, this is the state machine, very simple one. But you see here, that's actually the indirect instantiation of this clock buffer, which is divided by 7. You see here, always complete direct instantiation here. And you see here, that's the I delay instantiation, and you see here it's in the channel. Well, in the channel actually we will see the instantiation of the iService. You see, that's always just a direct component, and you do instantiation, you connect this. So now my my test bench here looks like this. I do have here again that's the interface itself. That's the model of the ADC. Very simple one, a few lines of code. This again, the same sensor model here, and that's actually the connection. Now, let's run the simulation here. Here you go. Okay, so now you see, that's actually the analog sensor. Which, well, let me run a little bit more here. You see, that's actually the analog sensor. Now I just do the synchronization. You see, that's called the bit slip. So look to the application of this iServers, because this is actually the synchronization process. So now this is the state machine try to synchronize to the sample. And now when synchronization is done, okay, then the frame, all the frames are valid, everything is done, and now the fiver gives the data. You see, that's actually now that's actually the input sensor, and that's actually the input, and that's actually the output. So this means if I do a little bit more, you see here, so that's actually the analog input sensor, and that's actually see also the sample rate here. So that's actually the output of the high-speed ADC, and that's actually, you see, the high-speed clock. This is the high-speed clock, and this is the this is the double data rate application. So we can actually see to the data and to the frame. You can actually see here. If I just do a little bit more zoom in, you see that's actually the high-speed clock here, and you see the data is center lined, double data rate, and whatever. Okay, and this frame identifies that's a sample, that's a sample, this is a sample, and this frame is read by the state machine and find out, oh, well, I'm synchronized, and I'm here synchronized, and now it starts. Okay, very it's very flexible. So this means it's a very good device. What actually was defined by the Xilinx engineers to do these kinds of design. Look to the training calendar in the material. So for example, if you let me click here, so in the material, it's in the bottom of your menu, you see the training calendar, all of the workshops you're offering. And let me just look here. And again, you can take them, you can scan the code here, and then you will get the link, or you get the access or a complete training portfolio. So I have the idea to again figure out what else can we do. Okay, so that's it. So thank you very much for your attention. And again, if you need more information, you have questions, just contact us, and we are happy to help and to serve. Okay, so thank you very much again, and goodbye.